Today I continue our grading with one paper appeared in the CGR 2018, and this paper named Improving Sequential Recommendation with Knowledge Enhanced Memory Network. So this one is the outline of my presentation. I just divide into four main parts. First, I will gradually introduce about the motivation, some definition of let's say sequential recommendation, item attribute, knowledge base, and memory network. And after that, I will present the knowledge enhanced sequential recommender model named KSE. Later on, I will talk about the experiment and the conclusion. So first, to begin with, I start with the second sequential recommendation for the one is not familiar with it. It means that assume that the one user, they adopt some item or they play the song. When we order by the time, we got a sequence. So the task when we want to based on his previous adoption or on his song and predicts the next song, we call it the sequential recommendation. Okay, actually there are two types of the sequential recommendation. One is the next item recommendation or next basket or next section recommendation, but in the scope of this presentation I just focus on the next item recommendation. Okay, so the common solution is like they trying to find some scoring function that to compute the score for all the items given the user and other time step. So here we have some G, U, I, T. U is the user, I is the item, and T is the timestamp T. Okay. There's recently we have some breakthrough result on the recurrent neural network, and GRU is one variant of the INN or recurrent neural networks. And here is a very simple GRU-based sequential recommender. First, we start from the adopted item sequence. So they used another they call it the embedding layers to estimate or infer the embedding for each item in each particular time step, and after that they will fit into a recurrent layers, and this one consists of many recurrent GRU units. And this one, the idea is they want to encode the sequential preference across all the item adoptions. Okay, and now after that, after we learn the sequence, we got this one we call it sequential preference representation for the next or the future's prediction. And for each candidate items, we also fit into the embedding area to get some the embedding vectors, and after that we using the inner products to compute the score for that candidate, and we rank all the items based on this score, and after that we generate the prediction, the next item prediction. Okay, so but actually beside it here we just based on the item ID or the identities of the items. But besides the identity, we have some other thing like we call it the attribute, or let's say we have some information about the artist, about the album, about the GRU, and this one is always come with for each individual items. And in real life, actually, from this additional attributes, we can generate some we call it knowledge-based entities or chiplet that we, let's say from this song we followed by the artist, we can add this song is performed by this one the artist, or another one is like this song is belong or in this album. So we have here we have entities, the relation, and another entities. So this one we call is a chiplet, and this one is the form of the knowledge base, that's the collection of the entities and the relations. Okay, and actually there are two very famous or popular knowledge base data is like the free base or Jago. This one is an ontology, but in this paper they using all the information from the free base. Okay, so we mean that we have a sequence, we can model the sequence with the GRU, but now we have the attribute that can be represented or provided by the knowledge base. So how we incorporate or integrate the KB in the sequential recommender? Actually, there's straightforward way mean that we can use it is the additional input according to the item. So we can have infer the embedding from each item and its relation or its information from the knowledge base. However, when we decompose the GRU, actually this GRU, this way have some limitation with the GRU or other RNN variants. It means that this one is the figures to represent how the GRU works, and each time we have some latent cell state or latent information here, but this one is just they present by vectors. So here is we have a limited short-term memories. Okay, another thing is like this one is just latent, so we cannot it present in the abstractive way, so we cannot to interpret the what exactly the user or the user intention for the in next time step. So with this, actually they can motivate us to think about another one is the enhancement with the memory network. It means that we increase the size, the memory size. The idea is just increase the memory size. Now this is the one vectors, right? And now we increase to in the array of vectors or a matrix. This one we call is a memory, and the memory networks, they support two operations. The first one is a read operations. The idea is mean that we want to retrieve all the related information to a given query. And another one is like after we adopt or we trigger a new action, we need to update, and this one is supported by the write operation when we update the memory based on some new action record are. Okay, and this one is the way the baseline model RUM use. I mean that they just extend the latent state size. Okay. However, this one still have some limitation in like. Okay, now we have bigger or larger memory state, but it's still in abstract representation because this one is in the black box, so we still need the latent, so we cannot easily understand and cannot to interpret the latent intention of the user. So in this paper, they propose a new or novel models. They call it the knowledge enhanced sequential recommender. First, this component is just come from the normal GRU-based recurrent the GRU-based component. So this one is to model the sequence. And after we got the sequential preference of the user, sequential signal. The main idea of this one, I think the most contribution part is mean that they consider the knowledge base as an external knowledge, and this external knowledge is modeled by using the key value memory network. And as you remember us, for the memory network, we need to read and write operation, right? For the read operation, we need to some query, right? And the idea means that they're using the sequential signal at the query to the key value memory networks to retrieve all the extra information that provided by the knowledge captured in the knowledge base. Okay, and after this part, we can get after this one the read, and the output of the read operation is we got some MUT. Here is they call it the attribute-based preference of the user at a timestamp t. Okay, and after that they combine both the sequential preference and the attribute-based preference with to get the PTU, and with the item candidate item representation Q tilde I, we can compute a score for each candidate items. So this one is the main idea, the overall idea. But I want to present more or detail about how they incorporate the knowledge base in the key value memory network. So first, starting from a knowledge base, so we have some chip list of the entities of entity relation and another entities. First, they're using the KB embedding algorithm. Here in this paper, they just based on the Chan E. This one is I will not go detail about this model because it's like the pre-trained model, so not a focus on the scope in this presentation. So they got some embedding for the relation and embedding for the entities. Actually, the main idea of this embedding algorithm is they try to minimize the distance between the embedding of the two the first entity with the relation minus the second relation. This one is similar idea at I think it's the man and woman and the king and queen. Yeah, actually after we got these embeddings, we're using it to initialize, or we initialize the key value network. So for each relation, we consider is respect to the one attribute, and they to use to initialize the key. And I want to emphasize that this key value is a fixed during the training of the proposed model. But for the value, they will based on both the relation and the entities to initialize, and this will be updated through the in the training. Okay, so now given one user U, they want to learn some the personalized attribute matrix, attribute value matrix. So here for each attribute, they have a V, A, and U. I mean this with the user and the attribute. And in the read function, this just as I mentioned before, this the way they want to retrieve the attribute-based user preference. And the idea means that now they for each attribute they will compute some weight. This one is similar like the attentional mechanism. They want to compute some weight for each attribute, and based on the how similarly the carry the sequential signal and the key value vectors, the key vectors, and after that they will sum over weighted sum over all the value. So we got the MUT. This one is attribute user preference. Okay, so now how we can update on these value vectors, the personalized attribute value matrix. Is that now if we have one new, let's say the user adopt the item I later on, so we can compute the the information that, or the embedding the information that the item, the information from the attribute A for the item I. So after that they compute the intermediate score here to update. This part is from the old value vectors, and this one is comes from the new, the contribution or the new information that when we trigger or we adopt the new item I. Okay, so we have read and write here.
So E1, E2, right? So what is the value? E1 or E2?
The value is the RA is the key, and the value is based on both the RA and E1.
E1.
Yeah, here because actually they say that maybe one item can have many attributes, right? So if we using the exact embedding of that item, maybe we can lose some information, or this one a general representation. So that's why they compute how much the item when we adopt the item given an attribute. Yes. So based on that, so mean that we need to base on both relation and the entity embedding.
So the value here include both entities in the relation or only one entity?
The value here is like here we write. For example, for this one is the attribute. This one is the relation, and this one is the value. The value here is we have two artists here. So we expect that, let's say for this user, this value for the artist, they will represent all the artists that the user that listen to.
But a relation has two entities, right? E1,
Yeah.
RA, E2.
Yes.
So for the relation artist, you have E1 and E2, right?
Yes. But actually, we don't use the artist. We don't use the exact embedding of the artist. We just infer the artist from the item. I mean the song and the relation. So that's why here this part. Is it clear?
So what is E1? What is E2?
E1 is two is just two entities. So for this, in this case, E1 is let's say the song.
Yes.
R is the album, or I mean is the play or sung by the artist is E2.
Okay.
But in this paper, they just make use of the E1, and E1 is mapped to all the items. I mean all the items in the dataset have a respective embedding, KB embedding. Okay.
So we don't actually care about E2.
Actually, yes. And we infer the embedding of E2 is based on the E1 plus RI.
It's exactly what we care for.
Yeah. I think that the thing in the value.
No, actually, but we don't use the E2 in when to change the KES.
E2 for some relations is E1.
But actually, in this,
the idea is like E and R somewhere contain information related to the E2, right?
So we receive the item, we build our recommendation not on the item itself, but on all the attributes.
No, they recommend songs, for example, right?
Yes.
So E1 is songs,
Yeah,
and the relation is artist. So it's
Yeah.
already contain information for other songs that related to the E1.
yeah.
So
So
you don't need E2.
the observation in each time step is the song, not the artist. So that's why we just concern the R here is a song, the embedding of the song. So we don't care about the artist embedding.
No, it's exactly what we care for.
Yeah,
We
yeah.
don't care about the embedding of
I
the
understand.
song.
I understand, but actually we need to minimize this way, right?
Yeah.
But in the training, this one we call the pre-train model. After that, we want.
So we don't care about the song itself.
Yeah, but the E1 plus R is already close to E2. So that's what the embedding
that is
minimized for.
questionable. That is questionable.
Why? That is
Because E2 can be relate. E1 can relate to E2, multiple E2s. So it doesn't mean that it's close.
But that's the point. That's the point. That's why they don't use the E2 here, but they need to compute that according to this. Because for each time, actually, for each adoption, right? Each adoption they can have, I mean, the different attributes. So that's why they consider this. And in this, and they just use this at the pre-train model and the fix. I mean, they will not update EI and even the RI. Okay. So after that, this one is the knowledge enhanced memory networks. So to make the score operation, I want to be more detail about it. First, let's say this one is a combination of the sequential reference, right? HUT here and the attribute-based preference. This way, this just simply concatenate. Okay, and for the item embeddings here, they concatenate the pre-trained embedding from another another model, the PPR. The QR here is the pre-trained vectors from using PPR, and the ER here is pre-trained vectors using the knowledge-based embedding. After that, they multiply with the PUT again. As I understand here is somehow the way it means that they try to use propose a function of the PUTs. This one is like the polynomial function of the PUT, and after that we can update or learn the correct PUTs. Okay, and the score is like this.
So how are the attributes related to the user? Why is it called MUT?
This one is the HUTs.
Yeah, the M. So how are these attributes related to the user?
For the value is the user personalized. This one is they train personalized metric of personalized vectors. So this part is users specific. So that's why MUT. But for the key, they share among the users. Okay. And for the loss function, they just try the pairwise loss with some negative sample. Okay. So this one I will not go details. So this is the main idea, the technical part of the model. So now I go to the experiment setup. The task here is the personalizing item recommendation. And in this paper, because they claim that in the dataset they have a lot of items, so that's why this is consider the candidate set include the graduate item and one negative items. So this one, the candidate set for each instant, the testing instance, that's 101. Okay. The data set, they consider the 4 data set with the statistic in the slide, but here actually I just show the ML 20 million and music. The evaluation in metric is MAP, the mean average precedence, MR, the mean reciprocal rank, hit ratio at 10, and NDC at 10. I just want to emphasize again about the pre-trained vectors. These vectors they fixed during the training of the KSE. KSE is the probable model. The item vector QI is infer using PPR. And the key vectors is infer from relation embedding. Okay, so this one is the pre-trained vectors and they fix during the training. For the compare models, they consider several baseline. The first one is BPR, is the latent factor with the relative comparison. The NCF is they reflect the inner product with the neural architectures. And the CKE, this one is they incorporate the KP, the knowledge base, and other information like suggest the image or text. And the FPMC, the factorized macro chain transition, and this on the GRU, this on the section-based recommenders. And they consider several variants of the GRU here with the GRU with the pre-trained embedding vectors, GRU with the KB embeddings at the features. And for the RUM, they consider two variants: the item level memory network and the latent feature level memory network. I think Maxime will tell you more about it later. This one the baseline, his baseline, and a little more. Okay. KS is the proposed model. Okay, this one is the overall result the comparison against the baseline, and we can see that if we compare with the RUM, the case is significant outperform, and the main idea is that like the KSE somehow they provide a flexible way to model the knowledge information, and another one is like it can compute the attribute-based user preference. And another line is the GRU. For the GRU, we also that the probable model is the upper form, and the idea is mean that the GRU is the reason maybe is the limited memory storage. Okay. So they do some the quantitative analysis when they consider this. When should we share or learn the personalized value metric for each users? And according to the personalized or private, you can, according to on the data set, they can see that okay, learning the personalized value metrics have some benefit, but the machine is not really big. And after that, they say that they will consider the share model to reduce the complexities of the model. Okay. Another one is like about the amount of training data. They try to save this using the subset of training data to learn the model and compare with the GRU++. And they say that okay, with more data, the KS is consistently better than the GRU++. The last one is they want to investigate how many latent dimension we should have used and what kind of the KB embedding algorithm we should use. And for the embedding side, they say that they can see that the 50 is best setting. And I guess according to the overall result, actually this one is somehow is for the movie length 1 million. So, but they did not state clearly in the papers. And for the compare different embedding algorithm methods, they say that okay, the chance is generate the signal the best result. So that's why they're using the Chinese for their experiment. Okay. So have one more or two more is a qualitative analysis. They want to show that their model can interpret the user preference. So first one for the attribute level interpretability. For this one is the timestamp. So for the first two, the first one is the attribute-based attention weight. The first one is because we don't have any information, so that's why we don't have a different signal here. But after that, we can say let's for the first two, we have some signal on the ambon. The second line is the ambon. The first one is the singer. So you mean that here the model somehow can capture. And for the next two, here, I mean that they will change the ambon, and this one they keep the same ambon. I mean that they have some signal, the sequential signal. They can capture the signal attribute-based signal on the ambon. But we just consider this part. Here, I mean the weight for the ambon is higher than the singer. But for this part, the attentional weight for the single attribute is get higher. So it represents like, let's say now we have the same singer, and the next the song at the time step 5, they also use the same singer. So this one and another like for the attribute now they reduce the attention, so that's why they may shift to the different ambon. So the author they claim that for this one they can model the mix between the the mixtures model of preference based on various attribute, mixture of the singer and the ambon. Okay. So for the value level interpretability, here that they say that if this one is this attentional weight, thus for that they want to when they listen on the same ambon or listen on the same singer. I mean this the attribute based factors. But now if they for each attribute they can have many items, right? Many options for respect to that attribute. So this part they try to showcase that scenarios when after we have the signal on the ambon and singer, we can very good prediction on the items or the song. So at the beginning, when we don't have any training staff, after some this one the ranking of the graduate item is low, and after the number of steps, the graduate item is pretty at the top one of the ranking. Okay. So this one show how the model can interpret the user intention. Okay. So to conclude, actually in this paper I introduced the knowledge enhanced sequential recommender model, K or KSE. The case is just simply the combine the GRU and the knowledge enhanced key value memory networks. Okay. The second one is case is the highly interpretable in both the attribute and the value levels, and the case is applicable to many domains. Okay, thanks.
Okay, unfortunately, we don't have time for Q&A, but we can hold our questions till the end. So now can we have the reviewer?